Welcome, ladies and gentlemen, to this video lecture. Let's take a look at this theorem. So let f be defined on an open interval containing some real number a, but perhaps not at a. Then the following are equivalent. The limit as x tends to a of f of x is equal to L. That statement is equivalent to saying that the right limit as x tends to a from the right of f of x is equal to L, and together with the limit as x tends to a from the left of f of x is equal to L. And you will notice here that this says what you have previously used, for example, in courses like 114, that the limit exists if the left limit and the right limit are the same. So this confirms that intuition. But now we can prove this using our rigorous definitions. And also what you should notice here is this word equivalent. These statements are equivalent, or in other words, A is true if and only if B is true. And remember, when you are proving an equivalence, you always have to do two things. So the first thing that you have to do is you have to prove that A implies B. Once you have done that, then you forget about that part, and then you have to prove that B implies A. So there are two parts. So I will not write down all the details in this proof. You now have all the tools in your toolbox to be able to write down the details of the proof. I will just discuss a sketch of this proof. So let's write here sketch of proof. First part, so part 1, A implies B. So what we will do is we will assume A, meaning the limit as x tends to f of x is equal to L. And remember, when we assume a statement like this, here we have a shop. We can buy, or we can bring epsilons, and we can get deltas out. So we can buy deltas at this shop. And then we want to show that the limit as x tends to a from the right is equal to L, and the limit as x tends to a from the left is equal to L. And remember, now we need to expand the meaning of these statements to be able to see exactly what we will do. So I'm just going to give a sketch. So for example, if the graph of our function looks like this, we are assuming that the limit of f is L, and now we want to show that firstly that the right limit is equal to L and that the left limit is equal to L. So what will we do? We need to show for any epsilon, so we fix any epsilon, and we look at this strip of radius epsilon around L. We take this arbitrary epsilon, we take it to our shop up here, and we buy a delta. This tells us that there exists a delta, so that if we look at all the values in that are within a delta distance of a, the function values all lie within this epsilon strip. And now we just forget about this part, because we want to show that the right limit is equal to L. So we just forget about that part, and we use the fact that all these values to the right of A map into this strip of radius epsilon of around L. And we repeat the same idea for the left limit. This would be a very good idea for you to try this, and perhaps if you are brave enough to post your work to the Discord. Okay, so that is the first part. The second part, so part 2, that here we now have to prove, so to prove B implies A. And remember, when you are proving this implication or this equivalence, these two parts are completely independent. You are not allowed to reference anything that you have done previously in either of the parts. So both parts are completely independent. Okay, so what will we do? We will assume B, which says that the limit as x tends to A from the right of f of x is equal to L, and the limit as x tends to A from the left of f of x is equal to L. And since we are assuming this, remember this is now these are now shops. We have two shops where if we bring an epsilon greater than 0, we can get out a delta greater than 0 that does something. And similarly here, we can pay with an epsilon, we can get a delta out. Okay, and now what do we want to prove? So to prove, we want to show that the limit as x tends to A of f of x is equal to L. So what will we do? So what are we assuming? We are assuming that the left limit and the right limit are equal to L. So we are in the situation like this. So if the graph of our function looks something like that, now we want to prove that this limit exists. Remember, we how do we do that? We expand the meaning of this statement, and we write a proof outline, and then we fill out everything. So what do we have to prove? We have to prove for every epsilon, if we look at this strip of radius epsilon around L. Please disregard the skewness of my sketch. So we fix any epsilon, then we take this epsilon, we can take it to this shop that will give us a delta that works with to the right of A. So we get out a delta, let's call it delta plus, that works to the right of A. So this is A plus delta plus. So all the values of x in here, all the function values take values inside of this strip over there. And we take our same epsilon and we go to the other shop and we buy a delta minus that works to the left of A. So, and these deltas need not be the same. So this is A minus delta minus over there, and all these function values, they map into or within an epsilon distance of L. And then what do we do? Remember, over here we must construct a delta, a specific delta. What do? We just take the minimum of two of delta plus and delta minus. So we set delta to be the minimum of delta 1, delta plus and delta minus, because if you are in here in this interval, then you're automatically in that interval. This interval is contained in that interval. So if you take any x in here, it is automatically in that in this bigger interval, and the function values take values inside of the strip that we are interested in. Okay, so that is the idea behind the proof of this theorem. Again, I would strongly suggest that you write out all the details, and by all means ask your fellow students to read your work, or the tutors or the lecturers to read your work and to give some comments on your proof. Okay, I will see you in the next one.